Okay, so last time we just sort of illustrated the use of illustrated with an example the use of randomized incremental construction, and the example was quicksort. Well, there are of course other known analysis of quicksort, but this is one of the more elegant one perhaps. So what we did was, just to summarize, we showed so we've visualized the choice of pivots as randomized incremental construction, or RIC in short. And we obtained what is already known about quicksort. I mean, we established the bound using this process, and the main tool for analysis that we used was this notion of backward analysis, right? Yes.
How do you obtain the permutation?
That was a question I posed to the class. So, are you asking me how do you actually obtain a random permutation?
Yeah.
Okay. So, perhaps I should actually assign this as a problem, but I will give you some hint. So, of course, any method for random permutation has to be randomized. There cannot be a deterministic method, right? So, what you do is you need access to some kind of random number generator, which is available in all programming languages. And the idea is, okay, I will give you the idea. So, the idea is that well, I mean, one is that you could the obvious way to do it is that you start with some so you have this, let us say you have an array of size n, okay, and then you choose any one of these, okay, and insert in another array. Of course, when you complete this process, so I find a random assignment for the first element, I find a random assignment for the second element, and so on and so forth. Now, this will produce a random permutation. So, whenever you have to develop a random develop an algorithm for random permutation, you have to first prove that all permutations are equally likely to be generated. Okay, so that is the first requirement. The second requirement is that, not requirement, the second desirable thing is to have something efficient. Okay, and where is that this process may not be very efficient is when you are choosing a random placement for an object. Okay, it may conflict, right? What is the guarantee that there will be a unique number produced? In fact, if you think about it, as you sort of, so you're finding a random assignment from the first element, second element, and as this array fills up, okay, the chances of collision or conflicts with an existing thing increases. So, this is also known as, I mean, a variation of this is known as a coupon collector's problem. Okay. So, so if you do the analysis, you will see that it will take about so if you just do this process, that take an element, find a random placement, and then if there is a conflict in the random placement, you generate another random number for that object, and towards the end, as I said, you will have to struggle more because the number of vacant places are reducing. Okay, maybe the last 10 objects, and if you are trying to place 1000 objects, you are going to really struggle to find the last few placements. So, if you do that analysis, we will see in the expected sense, you will do about n log n kind of calls.
I mean, when I get a random number, so between 1 to n, I place it there, and then I exclude it, and then among the remaining n minus 1 I do.
Okay, so then you have to have a random number generator with a different property. Okay, so here I was assuming I have a random number generator which will give me a random number between 1 through n, okay, or whatever, some fixed range. Now, if you there are ways where you can reduce that range. So, next time I need a random number generator between 1 through n. Now, there is a complexity of this random number generator also, because you are going to what you have available is a random number generator in a fixed range. Okay, that has to be modified. Okay, as the range shrinks, that has to be modified, and there is a cost for that also. Okay. So, there are algorithms, okay, where actually you take a random number generator and you can reduce the range. Okay. So, that's something called a dynamic random variate. Okay. So, there are algorithms for that also, and that also has a cost. Okay. So, you do not get it for free. Okay. So, what is given to you is a random number generator between either 0 to 1, which you can scale appropriately, or 1 through n, that that you have to sort of shrink as it goes on, 1 through n to 1 to n minus 1, and so on and so forth. So, for all that there is a cost that you have to pay, okay, in algorithmically. Okay. So, the one that I mentioned is the most straightforward one. I do not change the range, and I am going to generate numbers in that range, but there will be conflicts. Okay. So, to make this more efficient than n log n, so what I am saying, in the expected sense, it will take n log n, because the number of trials, expected number of trials that you need to find a random placement, okay, basically increases as you fill more and more buckets. Okay, and it's roughly about the number of trials will be about what, can you guess? So, the probability of success after you place the first one is n minus 1 over n, right, and then it reduces. So, the success probability reduces. So, the expectation is 1 over that. So, when you sum it up, it is just the harmonic again, n times harmonic. Okay. So, it is again n log n. So, there is a trick that what you can do, instead of placing these elements between 1 through n, you take a slightly larger array. Maybe you take an array that is twice the size, take an array of size 2 times n. Okay. And then you see that the probability of conflict, okay, is just about at most half. That is, when even when you have placed all, let us say everything but the last element, okay, there are still about n plus 1 vacant places, right. So, the chances of conflict is no more than half. Okay. And if you do the analysis properly, so what do you do? So, eventually you get a half filled array, right. You get all the n placements in an array of size 2 times n. Okay. And then what you do, you just shrink that array into. So, because the relative order is what the permutation is. Okay. And again you have to prove that it generates every permutation with the same probability of 1 over n factorial. Okay. And then you can compress it, and that's your permutation. And then if you do the analysis correctly, okay, here your success probability is always at least half. Okay. So, expectation is order n. In fact, you can prove something even much better, that with high probability it will be order n. Okay.
So, here you are generating random number between 1 and 2n, and then wherever it goes,
yeah.
you put it,
so, yeah,
and then
right.
you take the
Eventually, and finally, and I just shrink the array. I just throw away the empty places. I just compress it. Okay, so I have told you everything, but I will still probably just to make sure that you never forget this, or that this is a very useful thing. I mean, it's used left and right. I mean, but somehow it's never taught in a course, or somehow people miss out.
I mean, you have to prove that this is
Yes, of course, yeah. So, you have to prove that what you get is a random permutation. Okay, so coming back to this problem. So, the main tool used was backward analysis, which was the following, that when we are dealing with the ith pivot, okay, what is the probability that, so I will just write it again. So, so it is useful to analyze the probability that an arbitrary element involved in the partition right. This is basically the probability that we could capture using this analysis, that, and this turned out to be a very nice simple number, which was about I over n. Okay. So, for an arbitrary element, what is the probability that when we are dealing with the ith pivot, that element actually participates in that it gets actually partitioned by that pivot. Okay. So, that is what we analyzed, and now with the backward analysis we came up with a nice simple number of I over n, and when you sum up I over n from I equal to 1 through n. So, the total cost of quicksort per element summation over I over n. This is again log n. This is expected, of course. So, for the n elements it is n log n. Okay.
Shouldn't it be 1 by I?
Oh, sorry. What am I saying? I'm sorry. Thank you. 2 over Now, as I said, this bound has been obtained by other means also. People have analyzed in different ways and been able to get this n log n bound, but this is one of the cleanest analysis of quicksort actually known to me. And what the lessons that we want to take out of this is that for this very general process of randomized incremental construction, when we add the next element, okay, what is the total work that is being done? Okay. So, whether it is sorting. So, in the case of sorting, the structure that we are getting out of it actually is a search tree. If you think about it, the first element, it basically the quicksort defines a search tree. The first pivot is the root of the search tree, okay, and then the two partitions, again when you choose the pivots, they define basically the children of the root and so on and so forth. So, finally, when you have completed with quicksort, what you get out of quicksort is basically a binary search tree. And although this this analysis actually says that since no element is partitioned, or in the expected sense element participates or involved in a partition about log n times, the height of this binary tree, the expected height of the binary tree is only log n. So, it is a nice binary search tree actually. It is not one of those long skinny skewed binary search trees. It is a nice binary search tree where the height is about log n. It follows from the expectation, right, that since no element is involved in more than about order log n partitions, it means that you take any path from the root to a leaf node, that path has expected length order log n. In fact, one can prove even stronger bounds that with very high likelihood it will be so. I am not getting into those technical details right now. So, what you get out of this very simple process is also, or any kind of quicksort process, not just this, quicksort also leads to a basically a search tree. Right? But for other problems, in the other geometric problems, we will the structure may not be that simple. Okay. So, let me just point out a few things. So, one is that what happens. So, when the ith pivot is chosen, okay, the scenario just before that is, okay, we will view that as a kind of this whole structure as a kind of a graph. Okay. So, you look at these elements. So, there are n elements. Okay, and there are certain intervals. Okay. Right. So, these intervals initially you can to be so these intervals are being defined by the pivots. So, maybe this is, so these are elements x 1, x 2, x 3 all the way up to x n. Okay. Let me call these intervals I 1, I 2, I 3. So, when the ith pivot is chosen, okay, just before that, how many intervals do you have? You have chosen I minus 1 pivots. So, that will define about I intervals, right. Okay. Okay. And the remaining elements, so these elements are basically mapped to these intervals, right. A certain element belongs to a certain interval. So, it kind of defines some sort of a graph. Right. There is some kind of a graph before we insert the ith pivot. Now, when the ith pivot is inserted, what happens? One of these intervals splits, right? Maybe this interval splits. Okay. So, I3, okay, is now okay, so let me call it I3 prime and I3 double prime. So, this interval kind of disappears. Okay. So, if you look at this graph gets modified when we choose this the ith pivot. Okay. So, some interval gets partitioned, okay, other intervals are untouched, and the one that gets partitioned, this is not a good example. So, let me just put in a few more elements here. Okay. So, there are 3 elements in this interval I 3 before the pivot was chosen, the ith pivot was chosen. Once the ith pivot was chosen, these 3 elements basically will get redistributed into these 2 things, right. So, the graph now gets modified where we have, let us say, I 3 prime and I 3 double prime, right, and then these get redistributed. Maybe this gets. So, over the course of this, this adding more and more pivots, or in the course of the randomized incremental construction in the context of quicksort, you have essentially this changing graph, where finally it looks like each element belongs to one interval. Okay. That is the final process. Right. So, any intermediate process basically can be viewed or visualized as a bipartite graph. The bipartiteness is not important. I am just saying that this is a bipartite graph, okay, because it expresses the relationship between the elements and the intervals. Okay. The good thing, or so how did we actually do the analysis? We did the analysis assuming that the cost of the partitioning is proportional. Okay. The cost of the partitioning is proportional to the number of elements involved in that particular interval that is getting split. Right, whatever was the size of the interval, because we are redistributing exactly those elements. Okay. So, that is what we analyzed, that is the figure that we analyzed. Okay. We actually did not take care of any kind of data structural costs. We kind of assumed that in the algorithm, the behavior of the algorithm, the running time of the algorithm is actually proportional, okay, to the number of elements that are getting affected when the ith pivot was being inserted. Okay. Now, for some other kinds of applications, who knows, the cost may not be exactly the number of elements, but maybe 10 times the cost, maybe log n times the cost, or some such thing. Okay. But here when we did the analysis, actually that number actually only captures the fact, or that is true under the assumption that the cost of the ith partition or the ith pivot is proportional to the total number of elements that are actually involved in that. Okay. It is only the number that we are counting. We are not counting any other kinds of miscellaneous costs. Okay. Assuming that whatever algorithm we have, whether we are using a linked list or a kind of a array, we can actually implement that step in time proportional to the number of elements that are getting involved. If there is any more cost, with some associated data structure, that has not been accounted for. Okay. So, this analysis is true, and you can actually kind of justify that yes, we will be actually even whether it is an array or whether it is a linked list that contains these elements, we will be actually able to implement that implement that pivot, the ith pivot, in time proportional to the number of elements involved. Okay. So, the generalizations that we will be looking for when we talk about more complex problems, this is a very simple one dimensional problem. This is if you view it as a geometric problem, it's these elements are points on a line. Okay. Go to higher dimensions, talk about convex hulls, talk about Voronoi diagrams, talk about what else, triangulations, Delaunay triangulations, whatever, or even in higher dimensions, these are no longer points. Okay. These are something like objects. Okay. It's basically a relationship between objects. Okay. And what are these? What are the generalization of intervals? These objects could be anything, could be points, could be lines, could be segments, whatever. Okay. But what is the generalization of the intervals? Well, it will depend on the problem itself, okay, and how we actually go and define those intervals. That itself will be crucial, okay. In the common terminology for these intervals, in the general case, okay, they are called ranges, okay, and there will be something like a finite number of ranges. So here we are dealing with finite number of elements and finite number of intervals. That was very easy easy to define, or it's a natural thing to happen in the case of sorting. But when we talk about geometric problems, we will have to struggle a little bit to actually define formally what the ranges are. So ranges in this case are intervals, okay. Ranges in for higher dimensional geometric problems, could be something like triangles or quadrilaterals or some such thing, okay. Some subset of the Euclidean space, okay. So ranges basically are subsets of Euclidean d-dimensional space in the most general case. Okay. And so randomized incremental construction will maintain this kind of incidence information or relationship between the objects and ranges as we keep on inserting the object. Now these ranges, okay, will actually be defined in some sense by the objects themselves, okay. So how many objects define them? So all these things will matter, okay. The kind of ranges, as I said, could be triangles, trapezoids, discs, these are in 2 dimensions. In higher dimensions, they are the higher dimensional analogues of these things, okay. So the ranges, will define them depending on the problem, okay. So one is the kind of ranges, and also how do the objects define the ranges? Or how many objects, let us say, that is more important. So in the case of sorting, how many objects define an interval? 2, right. So an interval is basically defined with the left endpoint and the right endpoint, okay. So these are things that we will have to generalize as we deal with more complex construction process, okay. And then finally, the analysis again will be done like this, we will think about, you can think about the whole process like an evolving sequence of bipartite graphs, okay. As we insert a new object, okay, some old, okay. So in the general analysis, as we insert the ith object, okay, we will have to basically account for the following changes, okay. One is that some existing ranges have to be deleted, some of the old intervals disappear, okay. Some new ranges have to be created, okay. And when we do this, we have to reallocate, or basically we have to change these edges. Basically, some of these edges the old edges will disappear, the relationship between the objects and the ones that are affected, right. The ranges that are affected by this, okay, the ones that are deleted, those objects will have to be now redistributed to the new ranges, okay. So objects have to be redistributed, right. And then, so you can see the real cost of the ith step comes from this step, the third step. In the case of sorting, all those elements that were affected by the partition, okay, that was the cost associated for that ith pivot step, right. But in the general case, the objects which objects should be redistributed, if some of these ranges disappear, okay. So suppose these were some of the existing ranges, okay, and these were the objects. Okay. Now, there is one more thing that can happen which we did not consider. So, in the case of points and intervals, a point was associated with a single interval. Okay. Now, when we generalize, it may be the case that a single object, it may not be a point, it may be a line or a segment, it can actually maybe intersect more than one range. Okay. So, you will no longer have the simple nice 1:1 mapping, but you could have a situation like this, the same object, okay, can belong or can be associated with more than one range. Okay. So, therefore, when the changes happen, when some of these things disappear, so suppose this disappears and this disappears, okay, you have to basically look at how many of these edges are affected. So, all the edges incident onto the ranges that are going to be deleted, they are the affected edges. So, we will have to count the total numbers of such edges, right. So, some edges will be deleted, okay, namely the ones associated with the existing ranges. Sorry, sorry, not existing, the ranges that are getting deleted. Okay. So, those are going to be affected, and then there will be some new ranges that are created. Okay. So, maybe some new ranges will be created, okay. And so, these will essentially will be reallocated or reassociated with some of the new ranges, okay. And so, these will disappear. So, those edges are affected, okay, and there are some new edges, okay, which may basically be incident to the new ranges, okay. And so, if you look at the structural changes in the graph, we will have to account for the edges that are deleted and the edges that are created. Okay. In the most simple case, we should count both of them, the edges deleted, the edges created, right. So, the structural change in the ith step, okay, is number of edges deleted plus number of edges created. This is the ith step, okay. And then when we sum this up over all the, so total structural changes, okay, will be basically over all insertions, ith insertion, okay, and the same thing, number of edges deleted plus created, okay. Now, here I claim that the first term, that is number of edges deleted, okay, is something that I can forget about. Why is it? So, right, an edge can only be deleted once, right. So, we can charge it to when it was created, and it is not going to affect the overall analysis, right. An edge can only be deleted once, and if it is deleted, it must have been created at some point of time. Okay. So, that cost of 1, okay, is not going to make any change, it is just show up in some constant factor. So, asymptotically, or let us say in the amortized sense, okay, we do not lose anything. So, we can completely forget about the first term, number of edges created, and we can claim that the total structural changes, okay, is the total number of edges created over all the I insertions of the randomized incremental construction process. Right. So, this is the way we are going to analyze the overall cost of the randomized incremental construction, and of course, we are looking at the expected cost. So, we are going to look at the expected number of edges created. Okay. So, okay, this is another thing that I mentioned before, assuming that the algorithmic cost is proportional to the structural changes of the, so this is called the conflict graph. Right. So, once if we assume that there is no additional data structure cost, it is only the changes in the way the elements are associated with the ranges is what is the crux of the analysis, or basically the that what determines the total running time. Okay. Then we have that total expected cost is nothing but over all I steps expected number of edges created in ith step. So, this is the overall scheme of things for analyzing the randomized incremental construction. Okay. And the quicksort was a very special and a very simple example of that. Now, for this generalization, I will have to introduce some definition and terminologies. Okay. So, I will go ahead and do that, and for that I will actually use some pre-prepared slides that I have often used for giving talks on this topic. So, simultaneously with that I will use I'll try to do, I'll give you some commentary and explanation, but those figures are much better drawn than what I'm going to do right now. Okay.
So, in the quicksort case, in the conflict graph, and at the final stage, say, so we had a very nice one-to-one relationship that one element will correspond to one internal exactly.
Right.
In the general case, is there always such a nice relation we find, or
no, but I just mentioned that we are actually going to deal with situations where the same element, the same
state, right?
Huh? No. It yeah. At any juncture, the same object could be associated with more than one range. So, the generalization is a true generalization. We do not have any. We are not dealing with any special.
Exactly.
I beg pardon?
Yeah, even in the finals.
Yes, it could happen that way. Could happen that way, not necessarily, but it could happen that way. Actually, in the final stage, what happens is the following. So, as we go through the definitions, these kind of things will become clearer. Once you have added all the objects, okay, then this notion of association, kind of becomes redundant. Okay, we have the final structure. Okay, so the notion of association kind of becomes redundant at that point. Okay, before I go into that, let me give you another nice example of illustration of backward analysis. Okay, so a slight digression for 5 minutes, but I think it's worth it. So here is this problem that is very well known, right, in the linear programming problem, and you can view this. It is very much a geometric problem. So your constraints are basically inequalities or hyperplanes. Hyperplanes define the constraints with the what do you call it, the half spaces. The half spaces basically are the constraints, right? And what is being shown here is that it's just a two-dimensional case of the linear programming where all the constraints are half planes, okay, and this convex polygon is the feasible region. Okay. And you can always assume that I think we had discussed this briefly before, that you can assume that I do a rotation of the axis so that the objective function that I am trying to, let us say, maximize is exactly the y axis. Okay. I am finding the topmost point. It's some arbitrary, of course, function, but I can just rotate the axis so that I am trying to find the topmost point of the convex polytope. Okay. And I think I had mentioned this in the context that although the feasible region is a convex polygon or a convex polytope, the answer to the linear programming is only just one vertex of that polytope. I do not need that entire polytope. I don't need to construct the entire polytope. In fact, it will be a disaster if I try to construct the entire polytope, because we now know that the size of the polytope can grow exponentially with the number of constraints, right. So, we do not want to do that actually. Right. So, this is a very simple geometric view of this problem, that we are trying to maximize xd. The coordinates are x1, x2 up to xd. Right. And what we are going to do is basically, okay, let us also assume that exactly, so d constraints define the optimum. In this case, two constraints define the optimum, and this will follow if we assume that no three lines intersect at the same point, no three lines are concurrent. So, this is again an assumption we are making. Even if they are concurrent, we can still handle it, but just it becomes a little bit more messy to do the analysis or explain. Okay. So, we have the nice case where all only two lines intersect at a point, okay, and the optimum is essentially defined by two such constraints, because it's a vertex of a convex polygon. Okay. In d dimensional, exactly d constraints define the topmost vertex. Okay. So, finally, or even if someone told me that okay, here are the d constraints that define the optimum, okay, can you verify it? So, suppose I give you this, I give you a set of constraints and tell you, okay, here are the d constraints that actually define the optimum of the linear program. Can that be verified?
So, you take two lines for half planes at a time and see their intersection is one of those.
No. So, so in this case there are two lines that define the optimum, okay, and suppose I just give you those two lines and say that the intersection of these two lines is what the optimum is for the linear program. Can that be verified quickly?
So, on one side of the thing, one side of the intersection,
Uh-huh.
there will not be any point of the convex polytope, right? That is the defining point of the
On one side of the
on one side of the vertex solution, there will not be any part of the polytope,
But
right?
is that not true for any vertex?
So, the optimal solution will be one of the vertex, right. So, we can check for the vertices for that.
no, but that will amount to computing all the vertices. I do not want to do that. Can I simply just verify? Well, it is not clear, but one thing we can certainly do is that we can certainly check if that vertex is a feasible vertex. Okay. Because I can simply check whether it satisfies all the constraints or not, and that is a quick check. Right. So, we will kind of be basically using that observation. So, we will run this incremental construction kind of algorithm. Let us assume that we generate a random permutation of the constraints, okay, and pick up some, let us say in this case two of these constraints, they will define an optimum, okay, and then you add the third constraint and the fourth constraint and so on and so forth, and if necessary we have to recompute the optimum. Okay. So, let us run this. Okay. So, this is my first this is the first vertex that I computed from the two arbitrary constraints, you know.
Sir,
That-
if we take points on the two lines, neighboring points, it will be a local maxima in the neighborhood. And if it is a linear programming, or the local maxima will be global maxima.
I am not sure what you mean here.
I mean, at other corner points, the neighboring points on those lines will not be local maxima. I mean, the other corner points.
Which other corner points are you talking about?
I mean, in the polytope,
Mhm.
the other corner points which are there, those corner points will not be local maxima around its neighborhood for that given objective function.
Let's take this offline. I'm not sure what you mean here. Let's continue with this. There is something about local and global optimum in the case of linear programming. Of course, that is what makes the problem work the algorithms work efficiently. But I'm not sure what you mean here. So here is my first step. I have taken two arbitrary constraints, from that random permutation. These are my first two constraints. Okay, generated this. Then I add the next constraint. Okay, consider the next constraint. Now the next constraint, somehow doesn't see in the if this optimum satisfy the next constraint, so like this one. Okay, so sorry. So the optimum that was on the previous optimum, if it satisfied the next optimum, then we could have continued with that optimum, right? Right?